We've been talking about this concept called momentum. First question, although you don't have to memorize it, it's worth memorizing because you get sick of looking it up. Momentum is what times what? It's mass times velocity. It's a vector. You're going to see direction is going to play a hugely important role this unit. Momentum next year is probably the most direction-filled unit you'll do all year because we can use momentum, you'll see in a few days, to analyze collisions and car crashes. And most car crashes are not head-on. They bounce off of each other. Or hockey body checks bounce off of each other. Anything that collides can be analyzed with momentum. You're going to see, Jenna, momentum also gives us a slightly different way to think about force. So we said momentum was really how much motion an object had. The faster it was traveling, the heavier the object was, the more motion it had. Really, the more oomph you need to bring it to a stop. Or if it hits you, the more damage it would do if you absorbed all that momentum all at once. We said the units for momentum were kilogram meters per second. We also said momentum could be measured in Newton seconds. I think I mentioned, Taylor, they're talking about naming this unit here in Einstein because it's a mouthful to say kilogram meter per second. They haven't yet, so maybe. We talked a little bit about big momentum and small momentum. We said, you know what? Anything in double digits, if it hits you, you'll go, owie. Okay, if it was around 99 kilogram meters per second squared, that might be enough to break a bone or something like that. But most of the time, if you absorb that momentum in a short amount of time, it's an owie. Anything in the hundreds, it's probably go to the doctor. Anything in the tens of thousands, it's probably, well, no, I lied, Christina. It's really how fast you absorb all of that momentum as well. And that's why we started thinking about momentum in a different manner. We started thinking about impulse, change in momentum, the amount of momentum that you absorb if you're hit by something, or the amount of change in momentum a moving object undergoes. And we found, Haley, that it also depended on time. In fact, another way to think about force, this is what Isaac Newton actually wrote the force equation as, don't need to write this down, but he actually wrote F equals change in momentum over time. That simplifies to F equals ma. If you take change in anything, what's change in anything? It's final minus initial. It's the final thing minus the initial thing. Be careful you don't do it the other way around, or you're going to get the wrong answer. Okay, you'll get an opposite answer. So it's final minus initial. If you found the final momentum minus the initial momentum and divided by the time, that also works out to ma. That's what Newton was really interested in. This is the impulse equation. We said it was sort of three equations in one. We looked at this question here involving a baseball, and we paused. So let's pick up where we left off here. Example 6. Example 6 says, what's the momentum of 112 kilogram football player running due north with a speed of 3.6 meters per second? Luke, since they gave me a direction here, I'm going to give you an answer that has both magnitude and direction. I'm going to give you a vector answer. Luke, what's part A asking me to find? Figured out where we are now? I know my audience. I know who's following along and who's not. He's turning pages. Figure it out? Okay, momentum is what times what, Luke? Okay. Which is what? $112 times 3.6. You said 403.2. I'll keep every sig fig this time for a reason. Although I'd probably just two sig figs. I'd say 400, but 403.2 units. Well, it's kilogram meters per second. Direction. Yeah. So now we're going to start to think a little bit about collisions. We'll do a whole day looking at collisions, but tackling is a form of a collision. So B says, what impulse must a tackler impart to the football player to bring him to a stop? What's another word for impulse? So it wants the change in momentum. Now, change in momentum, I said this impulse equation kind of has three equations in one. One of them, don't write this down, one of them said that change in momentum was equal to, oh, got a latecomer, going to have to pause the video. There's several ways, don't write this down, to think about impulse. One was force times change in time. Have they given me a force or a time yet? Do you see anything in newtons? Do you see anything in seconds yet? In fact, looking at part C, I noticed they gave me a time and they want me to find a force. Jen, I'll bet you that's what I'm going to use for part C. So, another way to think about impulse, I said, was it was mass times the change in velocity, so it was mv final minus mv initial. Have they given me a final and an initial velocity? You know what? I think there's an even easier way, and this is what you can write down. What's change in anything, Pat? You know what? Maybe I can just go momentum final minus momentum initial. What word did I underline, Darcy?
Stop.
If you're stopped, what's your momentum?
0.
So what's our final momentum here in any tackle?
0.
Okay? I think that's reasonable to assume, yes? Unless they missed the guy and the guy keeps running, but that's not a tackle. So 0 minus, Darcy, what was our initial momentum?
400.
Yep. And I get negative 403.2 kilogram meters per second north. That's kind of a dumb way to say this. What would negative north really be? Yeah, you know what? And this may seem really obvious now in hindsight. If you want to bring any object to a stop, you have to give it the same amount of momentum but in the opposite direction. And this is why, Luke, I said at the beginning here, direction is going to become much, much, much more important, because you're saying, wait a minute, you're adding 403.2 and getting 0? Yeah, you are. Yeah, because it's negative compared to north. Okay. If the tackle was completed in 0.8 seconds, what average force? Okay, now they want me to find a force. And for what it's worth, again, Lyndon, I could probably, don't write this down, I could probably go F equals ma, and I could probably find it, you know. What did I find, Lyndon, in part B? It would be cool if there was an equation that had impulse and force in it. And there is. It's that one. It's a nice little shortcut equation if I have already done a fair bit of calculating. Part C says find the F, find force. Lyndon, how would I get the letter F? How would I get the force by itself? First of all, I want the F to stay there, I think, yes? What's the delta T doing to the F? Adding, subtracting, multiplying, or dividing? So how will we move it over? Yeah, I think you said times. You meant divide, right? No one noticed. Okay, we're good. So you're telling me another force equation is impulse over time? And I said to you, time is always a delta. We're kind of sloppy. A couple of units ago, we stopped putting the triangle in front of time. Here, we put it in there just because we have a triangle on the left and a triangle on the right. It's symmetrical. It reminds us both of these are technically changing. Lyndon, what was the impulse? You know what? I'm going to write it as positive. And what direction will positive be? No, what direction will positive be in part B? South, okay. So if I get a positive answer, I'm going to call it? Yes. What's the time? 0.8 seconds. How many newtons of force? What was the average force? And again, Taylor, the reason I'm saying average force is I think when you tackle someone, I don't think the force is constant. I think the biggest force is right away, and then as your body kind of a little bit, that kind of cushions things and the force goes down. Anyways, I'm hedging my bets of being a physics nerd. So it's going to be that divided by 0.8. You get 504? That's why I wanted to keep all the sig figs. I knew this one worked out evenly. Newtons. Lyndon, did we get a positive or a negative answer? Direction? Okay. We, for some reason in part B, decided to let south be positive. Okay? I wrote here, although we solved this using impulse, we really could have done this by going VF equals VI plus AT. We could have got the A equals VF minus VI over T, and then we could have gone straight to F equals MA, and it wouldn't have been much longer. It would have been a couple of extra lines. So why do we even bother with momentum and impulse? Well, first of all, the main reason, Haley, it's the best tool we have to analyze collision problems, which is going to be the next lesson. But there are a few other questions that are most easily answered using impulse. Consider the following example. Turn the page. 2 eggs are dropped from a height h. You know what? H. That's a terrible H. Let's make it a little better. 1 egg hits the floor and it breaks. Splut. Good sound effect. The second falls into a pail of water and survives. What's the main reason the second egg survives? Yeah. What, I've heard soft, I've heard cushion. Physics terms, yeah. Well, Natasha, hang on, you get a candy. That was brilliant. Sorry, you used a physics variable. I heard it. What was that? What was that? Time, you say. To absorb the force, you say. Wow. You know, it would be cool. It would be cool if we had an equation that had force and time both in it. You know what? I think we do. I think it's our impulse equation. So let's start out with some concepts here. I think we're going to say this. Both eggs undergo the same change in momentum. Let me argue that with you. They both have the same mass. Let's pretend they're magically identical eggs. If we drop them from the same height, will they hit the ground at the same speed? Yes. And what would the final speed be for both of them? 0. So if the final speed and the initial speed and the mass are all the same, mv final minus mv initial, I'm going to argue, Linnea, they both have the same momentum. Same change in momentum. Fancy word for change in momentum that begins with letter I? Okay, they both undergo the same impulse. Now, Natasha got right to the root of the matter, and this also explains why, when I whomped Thomas upside the head with a little Nerf baseball bat, why it didn't hurt. Because there's another way to think about change in momentum. Another way to think about change in momentum is force times change in time. Draw a little line down the middle of the page like that. Now, both eggs are stuck with this same change in momentum. This collision here, where it hits the ground, how long does it last? A long time or a short time? So, for this situation, you have a tiny time. You must have a massive force to get the same change in momentum. But as Natasha pointed out, when it hits the water, what did you say happens to the amount of time? So, and that means you only need a tiny, tiny force to still get the same change in momentum. You must get a smaller force. If time goes, if you're stuck with the same impulse, the same change in momentum, if time of impact goes up, force goes way down. By the way, this explains, I wrote here, Mr. Dewick needs to pummel someone, but only for the sake of good physics. I already did that. The reason it didn't hurt is not because soft, that's not a physics term. The cushion, the foam, the softness lengthens the amount of time of the collision, which must make the force smaller. And it's force that actually is what we feel is our impact. This explains, Jenna, the difference between being in a car accident on the freeway, where your final momentum is 0 in any collision, and your initial momentum would be mass times whatever 100 kilometers per hour is in meters per second, and leaving the freeway, going on an off-ramp, driving onto a city street, driving onto a subdivision, pulling into your driveway, and coming to a stop. In both those situations, your initial velocity is 100, your final velocity is 0, but because you spread the time out over 5 or 10 minutes in the second situation, Brian, you don't even notice the force. It's near 0 because the time is so big. So, damage from change in momentum is not caused by how much momentum is absorbed. It's caused by how fast change in momentum. By the way, what's another word for change in momentum? Let's write above here, impulse. Impulse. And so I fibbed to you a little bit in this chart way back here that I set up really just to give you some interesting variables. This is really nonsense. What I should have also included in here, Luke, is how fast are we absorbing the momentum? Now, in all three of these, I implied it was collisions, which means you are absorbing it pretty fast. How many of you have ever played catch with a water balloon or an egg? How do you catch it? You catch it with your hands locked in place. You lengthen the time. You increase, you cushion it. Those are the words you've used, but I'm telling you the physics variable that you're doing is you're increasing the time of impact, lowering the force. Has to get smaller. Okay? Wow. Here's another way to think about the egg question. Why do they use bales of hay to line some racetracks, especially like motorcycle races or bike races? What's the advantage in being brought to a stop by a bale of hay instead of by a brick wall? You're still stuck with the same impulse, Lyndon, the same change of momentum, but you have a choice. You can have a longer time, smaller force, or you can have a bigger force, shorter time. And it's force that does the damage. In fact, it's acceleration that does the damage to people or occupants or cars or machinery or whatever. Okay? Is that all right? For athletes, yeah, next page. Is it next page? No, page over. In many sports that involve striking something, tennis, baseball, hockey, soccer, golf, players are told to follow through when they come in contact with the ball. Why might this help the ball leave with greater velocity? So a little sports physics for you. Why do we follow through? What's that? Another word for which is impulse, change of momentum. Okay. And another way to think about it is force times change in time. If you want the ball to go in the opposite direction as fast as possible, what you're really saying is you want to give it as big an impulse as possible. Okay? Now let's suppose you're a professional athlete, Jenna, and you've lifted weights, you have built up your muscles as much as possible. Suppose you have maxed out the force. What else is on the same side of that equation? Time. If I can lengthen the time of the collision by following through, by keeping the ball in contact with the bat a little bit longer, by keeping the racket in contact with the ball a little bit longer, by keeping my foot in contact with the soccer ball a little bit longer. Then we'll end up with a larger impulse. Now remember, impulse is also mass times change in velocity. It's terribly messy. I can do that better. Does the mass of the ball ever change? No. So if I've just managed to get a bigger impulse, you know what must have changed? Velocity. Any of you play tennis? Nobody? Okay. I played tennis growing up. To do a drop shot, you pull back just as you hit the tennis ball with the tennis racket. You minimize the time of impact that dramatically reduces the impulse. Rather than the ball going backwards, you can take most of its momentum away and it'll drop. Anybody play baseball? How do you bunt? Same idea. You try, instead of following through, you're trying to impart as little impulse as possible. How? You're trying to reduce the time and reduce the force by not swinging as well, but you're also trying to reduce the time. Okay. What has more momentum, a 1,000 kilogram car moving at 100 kilometers per hour or a 2,000 kilogram truck moving at 50 kilometers per hour? Momentum is what times what? Okay. Now, these units aren't quite right. It would be kilograms, kilometers per hour instead of kilogram meters per second. But just go mass times these velocities. What do you get? Connor, what'd you get?
100,000.
What about for the other one?
100,000.
So let me ask you the question. Which has more momentum? A 1,000 kilogram car moving at 100 kilometers per hour or a 2,000 kilogram truck moving at 50 kilometers per hour? Right? Have I got football players in this classroom? Or hockey players? This is the most... You play hockey? Okay. I was going to say this is the most unathletic classroom I've had in a while. Let's go back to the tackling question. You guys can stay where you are. If I'm a hockey player and I want to cancel out somebody's momentum, okay? If I'm heavier, I don't have to be moving as fast. If I'm lighter, I got to be moving faster. This is why defensemen are always taller and heavier. You see the odd, very small, like 5'8", 5'9" forward. Have you ever seen a 5'8", 5'7" defenseman? No. In football, the offensive linemen or the defensive linemen in particular have enough mass. They don't need to be going very fast to cancel out somebody's momentum. So we put them up at the front because they don't have time to get going very fast. If you're a small little guy, you've got to be going faster in order to bring somebody to a stop if you tackle them. Okay, not very profound? All right. Does a moving object have momentum? Momentum is what times what? Mass times velocity. If an object is moving, does it have mass? Yeah. Does it have velocity? So yes. All moving objects have momentum. Does a moving object have impulse?
No.
I hear yes, I hear no. The good news is one of you is right. Convince me. Change in momentum. So really I'm asking, does a moving object have a change in momentum?
Only if it's changing.
Pardon me?
Only if it's changing.
Only if what's changing?
The velocity or the momentum.
And how can the momentum change? Momentum is what times what?
Velocity times mass.
I'd like to say mass times velocity. Now, we are not going to look at the mass changing. Where does the mass change? Space rockets, as the fuel burns, what happens to the overall mass of the rocket? It gets smaller. That's actually a really difficult question to deal with. You really need calculus. So one way would be if the mass was changing, but the easier way would be if the velocity is changing. So does a moving object have impulse? Not unless the velocity is changing. In other words, if you're going at a constant speed, what's your impulse? 0. What's your momentum? Not 0. Little playground physics, you all figure this out when you're about probably 4 or 5 years old. When you jump from your lab table to the ground, or in the playground when you jump from one of the apparatus down to the ground, why do you bend your knees as you land? Can you tell me that in terms of, she said to absorb the shock. Can you tell me that in terms of physics variables? Increase time, which means lower force, because you're stuck with the same impulse. You still, Reese, want the final to be 0. You gonna make it, Reese? It's a long blink. I know. Welcome back. You had a long weekend. Okay? This is why you bend your knees on impact. Okay. Which of the following situations is more likely to knock out a boxer? Leaning back while taking a punch or leaning in while taking a punch? And convince me. Now, you probably know the answer. It's the why that we want to talk about. Which of these is more likely to knock out a boxer if you're leaning back while taking a punch or if you're leaning in while taking a punch? What do you think? Leaning in, okay? In fact, that's if you're a boxer, if you catch the guy leaning in, that's what you want. The real question is, so let's circle that. Why? Why?
Because he's decreasing the time.
Yeah. Just like the follow through answer above, when leaning in, T increases. When leaning back, T decreases. Time of impact decreases. You don't come in contact with it for as long. And so we're really now, you're starting to see, I think, why, even though we could solve all of this really, Patrick, with Newton's laws and VF equals VI plus AT, it's sometimes nice, especially when there's collisions involved, to think about force that having some kind of time component, and that's why the impulse equation here is so nice. It gets a force, it gets a change in velocity, and a time component all in the same equation. Michael, it really lets us think about what's going on here. Is that okay? What's your homework? I already assigned 1, 2, 3, 4, 5, 6, 7. So now you can handle number 8, number 9, number 10. I already said you could try 11, 12, 13, 14. You're going to end up doing everything. 15, 16, 17. And I think I have a